What are the limits of digital to analog conversion fidelity? Imagine trying to recreate a perfect sound or image from a digital file. No matter how advanced your equipment is, there are always boundaries that shape how true that reproduction can be. When it comes to digital to analog conversion, or DAC, these limits are rooted in the core principles of electrical engineering and signal processing. Let's explore what really sets the boundaries for how accurately a digital signal can be turned back into an analog form. The first major factor is resolution, which is measured by the number of bits used in the DAC. Think of bits as the steps in a staircase. More bits mean more steps, leading to finer detail. For example, a 16-bit DAC can produce over 65,000 discrete voltage levels. But because the levels are finite, small changes in the original signal can get lost or approximated. This introduces what is called quantization error, which limits how precise the output can be. The more bits you have, the smaller these errors become, but you can never completely eliminate them. Next is the sampling rate, which is how often the digital signal is converted into an analog signal each second. According to the Nyquist theorem, the sampling rate must be at least twice the highest frequency in the original signal. If it's too low, high-frequency details get lost or create artifacts called aliasing. Increasing the sampling rate allows the DAC to more accurately reconstruct the original waveform, especially for signals with rapid changes. Linearity is another key factor. It describes how well the output voltage matches the digital input across the entire range. When a DAC is linear, a small change in the digital input results in a proportional change in the output voltage. But imperfections in components, like resistors, can cause nonlinearity. This distortion means the output doesn't perfectly follow the input, reducing fidelity. Electrical noise and distortion also play a role. Noise is unwanted electrical signals that mix into the output, lowering the signal-to-noise ratio. Distortion can happen during the conversion process, especially when the DAC switches between different levels. Glitches or imperfections in output buffers and filters can further degrade the signal quality. The bandwidth of the reconstruction filter is another limit. When a DAC outputs a step waveform, it needs a low-pass filter to smooth it into a continuous signal. The filter's bandwidth determines how well high-frequency components are preserved. If the filter isn't perfect, it can cause attenuation or aliasing of these components, affecting the overall fidelity. Finally, the speed of the DAC influences how well it handles high-frequency signals. Faster DACs can convert digital data more quickly, enabling higher sampling rates and better temporal resolution. But faster speeds often come with increased noise or more complex circuitry, which can also limit the quality of the output. In real-world applications, these limits are balanced based on the needs of the system. High-fidelity audio systems use DACs with high bit depths and high sampling rates to capture every nuance of sound. Simpler embedded systems might settle for lower resolution and slower speeds to save costs and power. So, the fidelity of digital to analog conversion is limited by the finite number of output levels, the sampling rate, linearity errors, noise, distortion, and the filtering process. Understanding these factors helps engineers design better systems that produce more accurate and reliable analog signals from digital data.